Okay, Sunday morning, April 5th. I have learned over the last couple nights that sometimes they don't record even after I've finished all the way to the end, and I lose them and have to do them over again. So I've decided I'm going to go ahead and write it out, and I think maybe later on I might just use my wife's notes and make annotations with that so that I don't have to restart and rewrite most everything and talk about everything. So anyway, we're about to introduce the idea of double integrals. And the thing that you're going to be finding with double integrals, first of all, is how do you do it? That's what I want to show you first. And what does it mean after we show you how to do it? Well, let me move this up because this is what I want you to see right here. You have to work with one portion of the integral at a time. So you're going to do that and do your fundamental theorem of calculus to plug in those boundaries. And then once you get that result, you're going to go ahead and take the antiderivative with respect to y. So again, as you do this, when you do the dx, you treat the y's like they're constants. Alright, and again, since I've lost some of this, I'm going to try not to butcher this all up in case I have to use it again. So anyway, if I take the antiderivative of this with respect to x, that's going to give me the result that you see right here. And as I go, I simplify some things. The 2 and the 4 can be reduced. So that's where that 2 comes from. And then I plug the upper boundary in first, and I plug the lower boundary in next. So here's the calculations. I think that I've done them correctly, but I'm sure you'll let me know sometime on a video. On a Zoom if you have that happening. And then I try to show with the double negatives or the minus to do the plus the opposite here. And so you end up with this expression minus this expression, and you add things together ultimately, and you end up with this. Alright, then you take the integral of what I just have underlined in yellow right there, and here's your integral now. And then I went ahead and reduced before I did anything, and you plug in the numbers. And so plugging in the numbers, you end up with this answer right here. Okay, so your answer for this double integral is a negative 117. That's the process that you follow. I'm going to count to 5 and then move on. Okay, here's another calculation. I don't really like it because the fact worked out to be 0, but that just happens to be what it is. You're going to take the antiderivative with respect to y first, so you treat the x's like constants, and you end up with this integral right here. And you plug in your 0 as your upper boundary and your negative 2 as your lower boundary, and you end up with this simplified version. Actually, it simplifies more to this. And then you take the integral with respect to x, and you end up with this, and then you do the fundamental theorem of calculus and plug numbers in, and it turns out that that first number happens to be a negative 18. So you end up with the 18, negative 18 plus 18, and you get a 0 for all that work that you've done. Alright, let me pause. Okay, I'm going to go ahead and talk about this one and the next one, and then I'll show you what it all means. But here's another way to say dy dx or dx dy and how you translate that. I will talk to you more about this. Okay, well, actually I think I'll talk about it right now. So if you were to graph all the x's between 0 and 4 and all the y's between 1 and 2, you'd end up with this little black box that you see over here. And the way this particular one is set up, because we did a dx and then a dy, the dx is going to be the boundaries that you have here and here. So remember right minus left for that. And then the thickness here is going to be a dy. And that's going to be how far you have to slide this thing. This thing's going to slide from a 1 to a 2. So that's the things you have to get used to when you're trying to translate these things. And the way this one is set up, because they have the dx, dy, the dx is the right minus left. Okay, I don't know where to write that, so the dx is the right minus left, so that's why it's a 0 and 4 for your boundaries. And then the dy is how far it slides. So it's how far this representative rectangle slides. If you've had Calc 1 with me, you know what I'm talking about. If you haven't, then we're going to hopefully get you squared away at some point in time. So after that, then it's just a matter of, I did a little algebra first before I took the integral. I went ahead and took the antiderivative with respect to x first, because that's the inner one right here. So I got this result, and I plug those things in, and I end up with basically what amounts to 16/3 y to the negative 2. And if you integrate that, you're going to get 16/3 y to the negative 1 times the negative 1 times the reciprocal. And then you plug in the boundaries 1 and 2. And so when you do your calculations, you end up with this 2 to the negative 1, 1 to the negative 1, which gives you a half minus a 1. So you have a negative 16/3 times a negative 1/2, and you get a positive 8/3. So this is the calculation for that particular setup. And again, I'm going to tell you what this all means real soon. One more example of the same problem, but doing it the other way, where you have the different orientation of the dy dx, a different order. So what this means is that this is the high minus the low right here. So here's the high and here's the low. And then the dx is going to be how far this thing slides. It's the thickness, and the numbers that you put are how far this thing slides to cover this entire region right here. So when you set this up, high minus low is going to be a 1 is the low and 2 is the high. This thing's going to have to slide, talking about this red or now yellow next to it, an infinite number of rectangles that are going to have to slide to cover all that region. That's going to have to go from 0 to 4. Okay, I'm not going to talk you through the whole darn thing. This just shows you get the same answer if you do it the other way as well. So you might ask yourself, why would I want it different ways? Well, I'll show you later that sometimes you can't integrate it one way, but once you rearrange the order of integration, it is possible for you to integrate it. I want to try to show you what it all means. And the first picture that I want to show you is this is your function. This is your three-dimensional surface. This is the red highlighted region right here that you see. And so what you're doing by those representative rectangles, at least one interpretation of it, is you're finding the volume of one of those, and then you sum up an infinite number of those that cover the entire region, and that's going to give you a volume. So a double integral is going to give you a volume, because the function that you have, let me start over again with that, because the function that you have is your surface, and then the area is going to be whatever this is with whatever the appropriate boundaries are going to be. But we really don't think of it in terms of summing up an infinite number of prisms, rectangular prisms like this. There's another way that we think of it that you saw in my pictures that I was drawing two-dimensionally. Okay, what we're doing in this situation, if I can make it a tad bigger, is look at the bottom one first. It's a good thing if I cough, I can go ahead and get something to drink and start over again. If you look at the bottom one first, that shows you, for instance, your rectangular prism that we were talking about before. And you have your dx and you have your dy. Well, if you put a row of those together, okay, look at this picture and imagine a row of these together. then in this particular drawing, this is the right function, this is the left function, and you have this representative rectangle that goes from right to left. And so if you're setting this one up, whatever the heck that function is, you're setting it up with a dy dx in this situation, because the thickness is going to be dx. So hopefully you can see this bright yellow. And so in our situation that you see in that particular picture, the one that is high is g sub 2, the one that's low is g sub 1, and then this is going to have to slide from A to B. And so when we're looking at this, that's the region we're concerned about. And when I actually set these up, you don't need to draw three-dimensionally, because all you have to do is be able to visualize what that surface boundary is below. And who cares what the heck this thing looks like? It makes no difference. You just have to figure out how you're going to set this up. Are you going to do high minus low and then slide from left to right? Or are you going to do, hope you can see this, you're going to do right minus left and slide up and down. Alright, that's what you're doing. You're finding the volume doing these double integrals. And then we need to talk about area at some point with a double integral, but anyway, let's go back. I'm going to pause it till I go back. Alright, so this is where I left off. And so you have a picture of the region that you're concerned about right here. I think I went yellow. So here's the region you're concerned about, and so it's just going to be this square that you see. And because it's a square, it's very boring in terms of setting it up in different fashions and changing the integration, the order of integration. But anyway, the way I'm going to choose to set it up, and I could have done it either way, it doesn't matter. I want to do this vertical representative rectangle that you see here now in yellow, but I'm going to get rid of the yellow. And so that means then the thickness is going to be my dx, and how far this thing has to slide to cover all of this, that's going to be my dy. So when I look at this, the high is going to be a 2 and the low is a 0, and then as far as how far this thing has to slide to cover all that, it's again a 0 to 2. Squares are boring. You don't have to make any decisions. You could be wrong and still get it right. So again, take the antiderivative with respect to y, plug in your boundaries, your fundamental theorem of calculus. Here they are plugged in. Simplify this, and I decided to work with a mixed numeral. So if you don't know how to do a mixed numeral, this is what I showed you right here. So I call it mixed numeral magic. Please don't use 0.333 repeating. Makes me want to vomit. So anyway, you get 29 1/3 minus 2x squared, and you want to integrate that. So this is just going to be 29 1/3 x, and this is going to turn out to be 2/3 x to the third, and you got to plug those boundaries in. Okay, move that up a little bit. So when I plug those boundaries in, I end up with this number minus this number. And so I did mixed numeral magic. I multiplied the 2 times the 29 and got 58, and 2 times the 1/3 and got 2/3. And it's kind of like the distributive property. I'm not going to fraction jail if I do that. And this thing works out to be 16/3, negative 16/3. So I have 58 2/3 minus 5 1/3. If I subtract that, I end up with 53 1/3, and there's our answer. Alright, count to 5. So this is just a review of, well, actually, this is what I guess my wife decided we should use to talk about the meaning of a double integral, which I've already done. So anyway, you have your boundary right here, and that's the high minus the low. That's what you would do if you were doing this for a just the area between the two curves. When you start talking about that portion right there and you do a double integral, you're pretty much forming this rectangular solid that you see here. This is the function, and then this is your dx and this is your dy, or vice versa. It really doesn't matter to me. So the volume of your prism is going to turn into this thing right here, which gives you those prisms that I talked about. Let me just go ahead and show you again. Gives you the prisms that we talked about right here before. Okay, but when we actually interpret this, we're going to sum up a row of prisms by doing our good old from Calc 1 method, the representative rectangle, and we'll just have an extra feature of high minus low, sliding left to right, or right minus left, sliding up or down and then up. This is all what you have to look forward to coming. Alright, so I don't think there's anything else for me to talk about here. Oh, there, my wife put the magic words here for you. You have a vertical representative prism. If you have one like this, then it's high minus low if you got some function. If you got a horizontal and you're doing this, then it's going to be right minus left if this is your region right here that you're worried about. Moving on. So what you need to do is interpret this notation right here. And so when I interpret it, that's what I'm doing with this. The y's are associated with the inner boundaries, and the x's are associated with the outer boundaries. Okay, let me erase that. So you're looking at it right here, and I think I want a different color. And so when you're examining this situation, you have your box that's going to be represented by these vertical lines and these horizontal lines. And because we did dy and dx, the thickness is going to be the dx, and the high minus the low is going to be the dy. So this goes from 0 to 2, and it's going to slide from 1 to 3. Alright, let's do it again similarly now. Same set of boundaries, except it's written the other way. So you have dx and dy. How does that translate? It translates like this. Because you'd have the x's would go with the inner one, and the y's would go with the outer one. That might be a good place for a different color. Okay, so let's just do completely different color now. This representation here is going to be what you see over here. And because it's dy, that is the thickness. You can't read that. Let's try a different color. That thickness is dy. That's slightly better. And what you have then is right minus left for what it's touching here and here. Okay, I think I'm going to get rid of that and try it with a different color. So let's do purple. The purple doesn't fail us. You'll have right minus left, and we'll have a dy as our thickness. Alright, so there's your setup for this situation when you change the order of integration. You say, why would I change the order of integration? Well, like I just said, there's going to be times you can't integrate it any other way. So remember from Calc 1, you have a vertical representative rectangle. Your thickness is dx, and you'd have high minus low for the length of this vertical rectangle. When you have a horizontal representative rectangle, the thickness is dy, and you're going to have right minus left to get the length of this, if you want to do it right, if you don't want your answer to be off by a negative. So we're supposed to sketch the region and I'm going to do something more than was being asked of us. We're going to go ahead and set this up like we're doing some kind of volume, and I don't really have a specified function, so I'm just going to do that sort of in general for whatever the curve or shape is above this particular set of boundaries. So I translated this set of equations this way. It's y greater than or equal to x minus 1 and y less than or equal to x squared. So I decided to use a vertical representative rectangle. So that means I have high minus low to get those values. The one that's high is the y equals x squared, and the one that's low is this y equals x minus 1. And then how far does this thing have to slide? Well, it slides from a -1 all the way to a 2. Can't see, I kind of destroyed the number, but there you can see the number again. So it's going to slide from -1 to -2, and that's your boundaries that you see right here. Now, I don't want to do it because it would be a pain in the you-know-what if I did, but if you decided to change boundaries, then what would happen? In other words, if you decided to do dx, dy, you would have a change in boundaries. You'd have a piece where you have this vertical line and this parabola as your boundary, and then you'd have this horizontal line, or excuse me, this oblique line right here, and this vertical line as a boundary. But then you got this little piece right here. You'd have to do 3 double integrals. You're out of your mind if you set it up that way. So you have to choose wisely which representative rectangle you decide to use. Alright, I'm halfway. I'm going to save this so I don't lose anything. So this is where we left off.